All right. So first thing we're going to start with is just some field equipment. You don't have to draw these. You don't have to write this down. It's mostly just, as your FYI, because when we're talking about the weirs, the purpose of the weir is to get a very calm waters so we can measure our stream flow. So this is just talking about measuring flow rate. Okay. So we would have in the field is this kind of tower here. It looks kind of like a little house. And then underground, there's some connections. And the connection essentially measures. So here is where we're measuring the pressure head. Okay. That information is passed back to the machinery in here. And this translates to a flow rate reading, because the piezometric head, or H, from years and years of gauging and measuring and measuring and measuring, there's a relationship between that piezometric head and flow rate. And so this kind of makes that calculation, and it estimates the flow measurement. Now, I mean, back then, that information was it was recorded on site, and then somebody had to hike into the site and download the data, very old school. Now they actually have an antenna attached to the site, and that is then transmitted to a local station. And so we get real-time measurements of flow rate. Someone's usually behind the desk to kind of make sure that the data makes sense. So these are kind of examples of what they look like. So this one's one of my favorites. This is like a little house. Okay, it's a little house on the side of the stream. So if you're ever walking in your favorite watershed and on your favorite trail, and you notice a house like this, that's most likely a stream gauge. This is also a stream gauge managed by the USGS, which is the United States Geological Survey. And this tower is actually very high up, because this is I know it's hard to tell, but this is a very, very large, very wide river. So the depth, the channel depth can get very, very high. So it's at a higher elevation. It's very high up to basically account for that. So it can get an accurate measurement of that piezometric head. So these are kind of examples of how you would measure that flow rate. I want to get into the types of weirs and what they're used for. So what you can't see in these pictures is that on the side of the river usually is where you would see this structure, which would be the weir. And so it's kind of showing here, this is the weir. Okay, so they're hand in hand. Where you measure the flow rate in the river, they're hand in hand. You would have some kind of some weir, some structure in the river to give us this ideal flow conditions. So the weir is an overflow structure. It backs up water so that flowing over the weir, so the flowing over the weir causes water to go through the critical depth. Okay, so I'm going to go into my notes, and I'm going to copy and paste some pictures to kind of fill in. Oh, actually, not with this one. I can just do a kind of a sample here. So here's the water backed up. Okay. And then we have this structure here. This would be my weir. Okay. And what's happening to the water as it approaches the weir, it actually starts, the level starts to go down. until it falls over the weir. So you have some flow rate approaching, right? You have some elevation of the water height above the weir. That's called H. Again, that flow rate is conserved as you're traveling over the weir. There's different types of weirs that you could have. So this is kind of a drawing of what's called a broad crested weir, but there are many, many types. So what I'm going to do is I do have photos of what those weirs look like. Okay, so this is the first type of weir. It's called a suppressed rectangular weir. What's different between the broad crested weir, which is very kind of a wide structure that I drew earlier, this suppressed rectangular weir is actually quite narrow. So this is an example here in the field of that suppressed rectangular weir. It's very thin. So it's a thin structure, and there's something called a nape, where the nape is that overflow, the width of that overflow. So the width here of your of your suppressed rectangular weir is about the width of the overflow. So that nape here. So again, super narrow. And as the water flows over the weir, somewhere around here, we have our critical flow. Back here, we have subcritical. And over here, we have our supercritical. Okay, so this is an example of the rectangular weir. The other weir, let's add some equations. So to calculate so typically what you would be calculating is either the flow rate. So the flow rate is equal to CW BH to the 3/2. So you would typically be calculating either the flow rate, or perhaps you're given the flow rate and you might be calculating H, where again, H is that elevation above the weir to the top of the water. So to calculate this, I have to provide some constants. So CW is CD to the multiplied by 2/3 multiplied by 2 multiplied by gravity, where CD is approximately 0.62. So this is a coefficient that's used to calculate that coefficient for the weir. So the only difference between the calculation is just going to be your gravity value. So there's some standard values where CW is approximately 3.334 BG units, or 1.84 for SI units. Okay, and CW is called the weir coefficient. B is equal to the base distance from crest to still water, which is not included in the drawing, but it's actually right here. So you have some distance B here. So in the problem statement, it'll typically say something like, how high should the weir be placed if we're to maintain an upstream depth of blah, 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 blah. Or we would say something like the distance from the flow measurement to the weir is approximately 5 feet. So that would be your B. Okay. Is the crest labeled in there? Oh, this is the crest, sorry. The arrow's cut off. That is your crest. So the distance from the weir to some upstream distance where we have some flow measurement, or where we have, some standard height of the water. Okay, so let's do an example using this equation. So we have a rectangular, sharp crested, suppressed weir that is 3 meters long, is 1 meter high. Determine the discharge when head above the weir is 150 millimeters. Okay, so we're in SI units, right? We're in meters. So that means our CW is approximately 1.84, okay? We're given that the sharp crested weir is 3 meters long. That is going to be our B parameter. And let's see, what else do we have? We have our head, this is going to be our H. So Q, which is CW BH to the 3/2, is 1.84 B, 3 meters. H, that's going to be 150 divided by 1,000 meters to the 3/2. So what is my flow rate going to be? 0.32. And that's going to be meter cubed per second. Okay. If you're not paying attention, I'll just let you know the next problem is not going to be this easy. Okay. So that's one type of weir. That's the, what did I say? The sharp crested suppressed weir. The next type of weir is a sharp crested contracted rectangular weir. Okay. For this particular weir, the crest is shorter than the width of the channel. Okay. It can have one or two beveled end sections. So water contracts horizontally and vertically. Okay, so here is a drawing showing these contractions. So this right here and this right here, these are our contractions. Okay, and it kind of shows you that there's this structure right underneath the water that causes it to again contract, it says vertically as well as horizontally. So it's contracting here and here. Now, it's not, you don't have to have two contractions. You can have one contraction, that's fine. You just have to make note of it because that does change your calculations a little bit. So the equation for the weir flow rate, it does not change. However, instead of B, it's B prime, specifically for the contracted weirs. So it's B prime H to the 3/2, where B prime is called the effective crest length, and B prime is equal to B minus 0.1 NH, where N is just the number of contractions. So it's 1 for a one-sided contraction, or N is 2 for a double-sided contraction. So if you go back to the picture here, this would be a double-sided contraction, okay? So N would be 2. Okay, so this can actually complicate things a bit, because if you put this beta prime into this equation, so you put this beta prime in here, then your Q is CW multiplied by B minus 0.1 NH multiplied by H to the 3/2. So when you distribute that H, this is going to be H to the 3/2 multiplied by CWB minus 0.1 NH to the 5/2. Do you see that? So if you have a problem similar to the previous example where H is given, if you know H, then this becomes a plug and chug. But if you don't know H, then what does this problem become? It becomes an iteration problem to solve for H. So I'm going to put a note here that if H is unknown, then you must iterate to solve. That is the contracted rectangular weir. We have 2 more weirs coming. So the next type of weir is a sharp crested rectangular V-notch weir. Again, the whole purpose of the weirs is to back up the flow, create this critical, we have subcritical conditions in the back end. We have critical conditions at weir, and we have super on the release side. Again, it's to get that controlled flow so we get a reasonable estimation of flow rate here, because we need that depth. We need to back up that depth in order to get a reasonable estimation of flow rate, right? Flow rate here is the same as the flow rate here, right? Via conservation of mass. Okay, so it just makes it easier for us to get that measurement. Okay, so this is our triangular V-notch weir. As you can see here, this angle is 90 degrees right here. So that is the most common angle. It's typically what we use for a triangular weir. It's designed, so we use these type of weirs for relatively small flows to, again, back up the head, back up the water, raise the water height so we can get a decent flow rate measurement. And the equation specifically for a triangular V-notch weir, Q, is CWH to the 5/2, where CW for this particular type of weir is 2.5. Again, that's for theta of 90 degree, if this is theta right here, for the triangular weir, and that's for BG units. And our CW is approximately 1.38, again for that 90 degree triangular weir in the SI units. Okay. Any questions so far about the types of weirs? We have one more to go. So the broad crested weir is exactly what it looks like here. It can be extremely large. It's incredibly useful for very large stream or long streams or wide streams. So it's used for So the equation to solve this is the same as the other CWBH to the 3/2, where CW is from the original suppressed rectangular weir is 3.33 for BG and 1.84 for SI. Okay. So this one, actually, the broad crested weir is the most commonly used type of weir for, again, larger rectangular channels. All right. All right. So that's it for the weirs. The next thing we're going to be talking about is a flume. So I've had a lot of experience using both the weirs and the flumes in the field. The flumes actually are the most common. And again, the goal is the same, right? With weirs and flumes is we're trying to control the flow pattern so we can get a good estimation of that flow rate. So the weir, it raises the elevation of water by backing up flow, right? The flume, it does the same thing. It raises the elevation of water by narrowing the flow. Okay, so a flume, it if we can have a kind of a diagram comparing the weir and the flume. So if we have a cross-sectional view, okay, of a trapezoidal channel, the weir is placed here. So this would be where your weir is. For instance, a broad crested weir. But when we're considering a flume, so again, we're going to look at that cross-sectional view. Okay. What we're actually going to be doing is narrowing. We're going to create a structure that narrows the channel. So this and this would be the construct of the flume. Okay. It's typically installed in the channel. So I'll draw kind of like an overhead view of what that looks like. So this would be as if it continued operating like a channel. And what you do is you install this kind of structure to narrow the path. Okay. So this would be the crest, for instance, of a weir. So you can do a combination of the two. I believe your book has an image. Where is it? It's on page 134 and 135. So it shows how we combine the weir and the flume to cause that flow to that depth to rise, so we can get a good measurement of that flow rate. So this is always the goal, right? Getting this flow rate as it passes through the flume and as it exits on the other side. Okay. So how do we calculate? So if we just have a flume, the most common type of flume is called a partial flume. Okay, again, it's the most widely used, and that's from the U.S. Bureau of Reclamation. okay? It's from fluid mechanics, we had done some calculations of maybe pressure differentials or velocity differences using a Venturi. Does anybody kind of remember that kind of analysis in fluid mechanics? So this is a Venturi type flume. You can kind of see that structure here. If you can remember, right, this was from fluid mechanics. We would have a pipe, we would narrow it, and then we would increase it, right? So this would be the nose. We would narrow it, and then we would allow it to release it. So the structure is very similar, except that it's an open channel, right? This is an open system. So to measure the flow rate in a flume, we would use this equation. Q is 4 multiplied by WHA 1.522 W raised to the 0.026, and this would be in CFS. So W is the width of the flume. So if we go back to this picture here, this is the width here, okay? And HA, HA is the upstream head, okay? So it's the similar upstream depth, okay? We could also have, so this is the typical equation for a flume. You can also, there's alternative equations for flumes for smaller structures, but we're just going to focus on the larger flume. So as an example, we have water flows through a partial flume with a throat width of 4 feet at a depth of 2 feet. What is Q? Okay, so we're dealing with a width of 4 feet and our depth, which is going to be HA of 2 feet. So we're trying to then find Q. So we would plug that into our equation here, where Q is 4WHA to the 1.522 W to the 0.026, okay? So Q is 4 multiplied by 4 feet multiplied by 2 feet raised to the 1.522 multiplied by W, which again is 4 feet raised to 0.026. Oops. This is one of those occasions where I have to tell you, don't worry about these units here in this equation. Does anybody know what this equation is called in mathematics, this type of equation? So this equation is based off of several experiments. So this is called an empirical equation. Sometimes empirical equations are based off of experiments. They're based off of, field measurements. They sometimes neglect the units that are involved by adding coefficients and things like that. So this is an example of that. So just know if your input is if your input is in feet, that's great. Your output for flow rate will be in cubic feet per second. Okay. So then what is my flow rate going to be? What is Q? 47.60 64, 76. I would say it's about 76 feet cubed per second. That's going to be our flow rate. Okay. Even if we're solving for our width, again, this will become an iteration problem because the width is in two separate locations. So the simplest approach is if you're given width of the throat and you're given the head of the water. But if you're not given the width, then this becomes a more complicated. Okay, so I had mentioned that there was, I have it. There was a diagram in your book that shows the combination of the weirs and the flumes. So I did actually copy that for the notes. And I added a few things to it. So this shows kind of the combination of our flume and our weir setup. So you can see that here's the channel, right? Here's the flow approaching, going across this way. And we're causing the water to narrow with the flume and rise due to the weir. And all of these attempts are always made to back up that flow so that we have our subcritical on the approach. So again, subcritical on the approach, critical at the weir, and supercritical on the other side of the structure. Okay?